Hello everyone. This video will cover my solutions to the problems of the day for this winter break that are posted on my Facebook page, which you can find the link to in the description below. Let's start with the first problem, which is problem number 18 of the 2013 AMC12A. Six spheres of radius 1 are positioned so that their centers are at the vertices of a regular hexagon of side length 2. The six spheres are internally tangent to a larger sphere whose center is the center of the hexagon. An eighth sphere is externally tangent to the six smaller spheres, and internally tangent to the largest sphere. What is the radius of this eighth sphere? We can start by first drawing the hexagon. So this is what the hexagon looks like. And we know that each side has side length 2, and that there's a sphere of radius 1 positioned at each of the vertices. So it looks vaguely like this. And here. And then there's a larger sphere, whose center is at the center of the hexagon, and who is internally tangent to the six smaller spheres. So we can draw the seventh sphere. And then now we need to flip the diagram 90 degrees. So the eighth sphere is going to be such that there are the two smaller spheres here, and then the eighth sphere is going to be somewhat like here, since we need there to be a circle outside of it. Now let's continue with the problem. Let's start by finding the radius of the largest sphere. We know that this is 1, and this is also 1, since this is an equilateral triangle. So the radius of the largest sphere is just 3. Now, transitioning to this diagram, we know that this length is 6. So we can find a triangle in order to find the radius of the sphere. And we can do that in this way. If we set this as the radius of the sphere, then we have r plus 1 and r plus 1. And we also know this is r. And if we just find this length, we can add these two together to get 3. But that length, if we can just find the triangle, is, so r plus 1, 2, and 2, because this length is 4. So this length is just square root of r squared plus 2r minus 3. Now, we can get a simple equation, which is r plus square root of r squared plus 2r minus 3 is equal to 3. And from this, we can rearrange and square both sides to get r squared plus 2r minus 3 is equal to 9 minus 6r plus r squared. And cancel the r squareds and shift some things around. We get 8r is equal to 12, or r is equal to 3 over 2, which is our answer. The second problem was problem number 21 of the 2014 MC12A. For every real number x, let this value denote the greatest integer not exceeding x, and let f of x equal to the floor of x, which is the term for that value, times 2014 to the x minus the floor of x, minus 1. The set of all numbers x such that 1 is less than or equal to x is less than 2014, and f of x is less than or equal to 1, is a union of disjoint intervals. What is the sum of the lengths of those intervals? So, although this problem looks quite complicated, we can simplify it with some manipulation. So, since 1 is less than or equal to x is less than 2014, we know that this value is always greater than or equal to 1. So we can transform this equation into an inequality. The floor of x times 2014 to the x minus the floor of x minus 1 is less than or equal to 1. And we can rearrange to get 2014 to the x minus the floor of x is less than or equal to the floor of x plus 1 over the floor of x. Or x is less than or equal to the floor of x plus the log base 2014 of the floor of x plus 1 over the floor of x. Now, we also know x is greater than or equal to the floor of x. So, the length of this interval is then just log base 2014 of the floor of x plus 1 over the floor of x. And we can find all of the floors that are possible. So this is between from 1 to 2013. And using the sum of logs formula, we get that this is log base 2014 of 2014 over 1, which we can get is just 1. The third problem was problem number 22 of the AMC 10A from 2019. Real numbers between 0 and 1 inclusive are chosen in the following manner. A fair coin is flipped. If it lands heads, then it is flipped again, and the chosen number is 0 if the second flip is heads, and 1 if the second flip is tails. On the other hand, if the first coin flip is tails, then the number is chosen uniformly at random from the closed interval 0, 1. Two random numbers x and y are chosen independently in this manner. What is the probability that x minus y, the absolute value of that, is greater than 1/2? Well, I think it will be easier to first calculate that the probability that the absolute value of x minus y is less than or equal to 1/2. So let's write down the cases for a possible random number. So if it lands heads, then it is flipped again. And if it's heads, then it's 0. And if it's tails, then it's 1. Now, if it lands tails, though, then it is the closed interval 0, 1. Now, what are the possibilities for this? Well, we can have HH, HT, or T in the interval, which I'll call I. And same for Y. So HH, HT, and TI. The only ways that these two can actually interact is for this value is that it happens this way, or like in this way, and this or this. So let's explore all of these combinations in the next page. So now we can analyze one case at a time. The horizontal cases are just half times half times half times half. So that is just half to the fourth, which is equal to 1/16. And we can multiply that by 2 to get 1/8. And then these cases are all actually symmetric. So we know that this is 1. So that means that I has to fall within half to 1. So this must be, again, half to the fourth. And this time there are 4 of these cases. So we get that this is 1/4. Now let's look at this final case, which utilizes geometric probability. So we have this graph here, and either one can fall within 0 to 1. Then we can look at this, and we know that in order for the difference to be less than or equal to half, it must fall within this region. The area of this region is just 1 minus half times half over 2 times 2, which is 3/4. So the probability of this happening is half times 3/4, or 3/16. The total probability that x minus y is less than or equal to 1/2 is then just 9/16. So the probability that the absolute value of x minus y is greater than half is just 7/16, which is our answer. Problem number 4 was problem number 23 of the 2014 MC12A. The fraction 1 over 99 squared is equal to this repeating decimal, where n is the length of the period of the repeating decimal expansion. What is the sum of all of these digits? So one of the easiest ways to do this is actually find what this is. So we know that 1 over 99 is 0.010101 repeating. So let's divide this 1 over 99 by 99. So we get 0.010101, etc. over 99. So this is 0.0001, then subtract 99, we get 201. So 02, then subtract 198, we get 301, then 03. And you can see a pattern, but let's analyze the pattern more deeply. So we have 0.0001, and when we find 01, the next remainder is 2, and that goes to be 201. So the next number is 102. Then the remainder after that is 3, and we add the 01. So this becomes 03. So this pattern actually continues all the way till we meet a number that is an actual multiple of 99. And this happens only at one spot, when it reaches 97. Then the remainder is 98, and we get 9801, which is the same as 99 squared. So it ends with 99. And this is the repeating decimal expansion. Now, the sum of this is just 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 times 10 plus 1 times 10 plus 2 times 10, etc. plus 9 times 10. This is just 20 times 10 times 9 over 2 minus 17, since we cannot have the 98, which equals 883. Next, we have problem number 21 from the 2019 AMC10A. A sphere with center O has radius 6. A triangle with sides of length 15, 15, and 24 is situated in space so that each of its sides are tangent to the sphere. What is the distance between O and the plane determined by the triangle? Well, one useful fact to note is that 3 points on a sphere determine a circle. So what circle is this? What relation does it have with the triangle? Well, we know that the circle is tangent to all 3 sides of the triangle, and it's contained within the triangle. So this must be the incircle of the triangle. And we know that this is 15, 15 and 24. So if we have the incircle, so this is 9, since this is a 3, 4, 5 triangle, then all we have to find is the radius, so which we can do by A equals RS, which equals 9 times 24 over 2, or 108. Then R, since the semi-perimeter is 27, R is just 4. So now we can easily find the distance, since the distance from a circle on a sphere with some radius is just, we can find it with the triangle. So we know that this is going to be 6, and we know that this is 4. So the radius is just square root, or the distance is just the square root of 36 minus 16, or 2 root 5, which is our answer. The next problem was problem number 15 of the 2013 AMC12A. Rabbits Peter and Pauline have 3 offspring, Flopsy, Mopsy, and Cottontail. These 5 rabbits are to be distributed to 4 different pet stores, so that no store gets both a parent and a child. It is not required that every store gets a rabbit. In how many different ways can this be done? Well, the easiest way to do this is to first distribute the parents and then the children. So the parents can either be together or separate. So if they're together, then we have 4 places to put the parents, and we can, for each of the other 3 rabbits, they can go to 3 places. And for separate, we have 4 times 3 places to put the parents, and then there are 2 places remaining. Now we can distribute the offspring in 2 ways. It can either be with 2 and 1, or it can be with 3. So with 2 and 1, we first choose which one is the 1, and that is just 3 ways to do it. Then we place that one, which is 2. And that's all we have, since the other 2 rabbits will be placed in the other store. And for all 3, this is just plus 2, since there are 2 ways to put the group in a store. And this evaluates to 108 plus 96, which equals 204, which is our answer. Problem number 7 was problem number 18 of the 2015 AMC12A. The zeros of the function f of x equals x squared minus ax plus 2a are integers. What is the sum of the possible values of a? So let's start by using the quadratic formula to find the roots. It comes out to be x is equal to a plus or minus the square root of a squared minus 8a over 2. We need a squared minus aa to be a square of an integer, so that its square root is an integer. So this is x squared. But a squared minus 8a is also a minus 4 squared minus 16, which is x squared. And 16 is just 4 squared, so we get a minus 4 squared equals 4 squared plus x squared. So we know that x, 4, 8, a minus 4 has to be a Pythagorean triple, or a degenerate Pythagorean triple. So x can be 0 as well. So the only possible values of x that make it a square are x equals 0, and then 3 or negative 3. And respectively, a is then equal to 0, 8, 9, and negative 1. So 0, 8 are for 0, and then 9, negative 1 are for the 3 and 3. So the sum of these values is equal to 16, which is just our answer. This problem was problem number 8 of the 1983 AMY. What is the largest 2-digit prime factor of the integer n equals 200 choose 100? Well, first let's write out what n is. This is just equal to 200 factorial over 100 factorial times 100 factorial. So we need a prime that shows up 3 times here, at least. Since if it shows up only 2 times, and it's 2 digits, then it'll be cancelled out by both of these factors. The highest prime that shows up 3 times is 61, and that's our answer. The next problem is problem number 8 of the 2004 AMY 2. How many positive integer divisors of 2004 to the 2004 power are divisible by exactly 2004 positive integers? Well, 2004 is equal to 2 squared times 3 times 167. Therefore, 2004 to the 2004 equals 2 to the 4008 times 3 to the 2004 times 167 to the 2004. Now, all we have to do is distribute these factors, these prime factors, among these numbers, since all of them are greater than or equal to 2003, which is what is necessary if we need 2004 factors. Recalling the number of factors formula, which is 1 plus a1 times 1 plus a2, etc., if the prime factorization is p to the a1 plus p1 to the a1 plus p2 to the a2, etc. Therefore, the number of ways to do this is 2 times 3 for the 2, since we can either have them together, which is 3 ways, or separate, which is 3 ways, times 3 ways for the 3, and then 3 ways for the 167. And this is just 54, which is our answer. Problem number 10 was problem number 9 of the 1987 AMY. Triangle ABC has a right angle at B and contains a point P for which PA equals 10, PB equals 6, and angle APB equals angle BPC equals angle CPA. Find PC. Well, first, let's draw the triangle. So we know that this is B, this is A, and this is C. And there's a point P such that all three angles are equal and are equal to 120 degrees. So this is P, this is 10, this is 6, and this is X. So we need to use the law of cosines in the Pythagorean theorem, since we know that AB squared plus BC squared equals AC squared. So we get that 10 squared plus 6 squared minus 2 times 6 times 10 times cosine 120, which is negative 1/2. So this cancels out with the minus 2 to get plus 1, plus 6 squared plus x squared plus 6x equals 10 squared plus x squared plus 10x. And we can do some cancellation, and we get that 4x equals 132, or x equals 33, which is our answer. This problem is problem number 9 of the 2001 AMY 1. In triangle ABC, AB equals 13, BC equals 15, and CA equals 17. Point D is on AB, E is on BC, and F is on CA. Let AD equals P times AB, BE equal Q times BC, and CF equal R times CA, where P, Q, and R are positive and satisfy P plus Q plus R equals 2 by 3, and P squared plus Q squared plus R squared equals 2 by 5. The ratio of the area of triangle DEF to the area of triangle ABC can be written in the form m by n, where m and n are relatively prime positive integers. Find m plus n. Well, we can start by drawing the triangle. So we know that this is A, this is B, and this is C. And this is D, this is E, this is F, this is 13P, this is 13, 1 minus P, this is 15Q, this is 15, 1 minus Q, and this is 17R, and this is 17, 1 minus R. So this is DEF. We can find the area of DEF relative to the area of ABC by finding the area of these three triangles. So for each of these, we can use the formula half AB sine C, which is the area of the triangle. So the ratio of the area of this to the area of the whole triangle is just Q times 1 minus P, using this formula. And similarly for the other ones, we get R times 1 minus Q plus P times 1 minus R. And we need to subtract all of this from 1. And this gives 1 plus PQ plus QR plus PR minus P minus Q minus R. So we need to find PQ plus QR plus PR, but we can find this easily, since we know that P plus Q plus R squared minus P squared plus Q squared plus R squared is 2PQ plus 2QR plus 2PR. And that value, the 2PQ plus 2QR plus 2PR, is equal to 2 by 45. And so PQ plus QR plus PR equals 1 by 45. And P plus Q plus R is just 2 by 3. So we get that 1 plus 1 over 45 minus 2 over 3 equals 16 over 45. So our answer is 61. The final problem is problem number 8 of the 2006 AMY 1. Hexagon ABCDEF is divided into 5 rhombuses, PQ, RS, and T as shown. Rhombuses PQ, R, and S are congruent, and each has area square root of 2006. Let K be the area of rhombus T. Given that K is a positive integer, find the number of possible values for K. Well, first let's assign a value of theta for this angle and A for this side length. Then we get that the area of Q, or any of the side rhombuses, is half A squared sine theta times 2, which equals A squared sine theta, which equals the square root of 2006. Now the area of T we can find with some more angles. We know that this angle is 180 minus theta, so this angle is just 2 theta. Therefore, we know that the area of T is half a squared sine 2 theta times 2, which equals a squared sine 2 theta, which equals 2a squared sine theta cos theta. But a squared sine theta is just square root of 2006. So this is 2 root 2006 cos theta. Now we know that 2 root 2006 cos theta equals an integer k. So cos theta equals k over 2 root 2006. And 2 root 2006 is a little less than, so this value is a little less than 90. So k must be less than 90 and greater than 0. So the number of possible values of the area of T is just 89, which is our answer. Thank you for listening. Please like and subscribe, and remember to click the bell icon for more updates.